The broadcast is now starting. All attendees are in listen-only mode.
Good morning, good afternoon. This is Mark Kovich, your System Sales Specialist at IBM. I'm part of the IBM Internet of Things continuous engineering organization, now called Connected Products. Thank you for joining the webinar today on Model-Based Systems Engineering Made Simple with Rhapsody. And today presenting is the infamous Dr. Bruce Douglas, Chief Evangelist at IBM. Before we get started, I'd like to mention you're in listen mode only and that this webinar is being recorded. We will have a question and answer session at the end of the presentation. I'd like to point out the question box in your control panel. Just click on that triangle where it says questions. It'll expand. You can submit questions that'll come directly to me, and I'll go ahead and ask them to Bruce over the audio portion here. Well, he'll go ahead and answer the question. Some questions will be answered by me directly. Also, if you'd like the presentation that Bruce is using today, it is available right now. Just go to the handout section of the GoToWebinar control panel where it says handouts. Click on the download button. You can get it immediately. Also, I sent a follow-up email, automated follow-up email to all registrants. Included in that email are a number of links where you can view the recording and also have access to the presentation. If you have any further questions or interests, you can go ahead and reply to me, and I'll go ahead and answer those questions or put you in contact with the appropriate IBM personnel that can assist you with any technical or sales needs if you require. We were just doing a presentation today, so Bruce will go ahead and start here momentarily. But before he does, I'd like to mention that I'm going to copy and paste the new archive site in the chat window. Feel free to copy and paste it yourself into your browser and save that for future reference. That's where we archive all the recordings of the Enlightenment Series webinars. So feel free to go ahead and view any of those webinars that we've done in the past. So with that said, we're going to get started here. Bruce, you can start.
Oh, thanks, Mark. So welcome, everyone. Today we're going to be talking about MBSE, made simple with Rhapsody, and how to address some of the common issues and problems, learning about MSE, adopting MSE, and adapting it to meet your needs. So today's quote, Law of Douglas number 136, comes from Bruce Lee. Knowing is not enough, we must apply. Willing is not enough, we must do. So he was channeling Yoda before Yoda was invented. So let's talk about what system engineering is to give us some context. Really, system engineering is about specification, architecture, design, and verification of system properties. It's not about software, it's not about mechanical engineering, not about electronic engineering, it's about system properties. So we don't focus on, for example, implementation, because those implementation technologies are done by specialists, what we call downstream engineering. We really focus on what are the requirements, system requirements, what is the architecture, how do we allocate responsibilities to different engineering disciplines like software, mechanical, and so on. How do we assess things like security, reliability, and safety? How do we do trade-offs between different technologies and different approaches? And then how do we hand off to those disciplines? So MBSE has some advantages over kind of traditional text-based approaches. When I talk about traditional approaches, I'm talking about text-based. So using Excel and Word as kind of the primary engineering tools, if you will. And there's nothing wrong with Excel or Word. Those are fine tools for what they do. But MBSE, model-based system engineering, offers some specific value. One is you've got the ability to create different stakeholder-specific views that are tied to this kind of single integrated engineering data set, which is what we call the model. And this ends up, you can do more precise and better specifications, because English or German or Chinese are wonderful languages, they're very expressive, but they're not very precise. They can be interpreted in different ways by different listeners. So there are issues about ambiguity, about precision with natural language. You have enhanced traceability among different work products that are all based on this kind of single source of truth. And so you'll have fewer defects and higher quality and less time to an equivalent quality. I've consulted to lots of projects, over 300 last time I checked. And this is a pretty consistent outcome, that you have higher quality and you have less time to develop that quality, or necessary to develop the quality. you end up with engineering data in these held in these work products, held in the model, and it's verifiable. If you've got all your data in Word as requirement specifications or in architectural notebooks, it's very hard to verify that, yes, that data is in fact correct as text, because text, again, is kind of an imprecise language. And again, you've got this integrated source of truth. So Agile and model-based system engineering, I think, are kind of collaborative technologies. Modeling allows me to specify things. We'll talk about this a little bit more on the next slide. And Agile is all about incrementally specifying and creating things, and incrementally verifying, continuously verifying things. And so when we talk about the interaction between modeling and Agile, what we really mean is we're incrementally creating engineering data, which shows up in work products, and we are verifying it in that information as well. So it's not we produce all this data and at the end they say, oh God, I hope this is right, and try to test it to verify it's true. As we create that engineering data, we are constantly demonstrating and showing, yes, this is in fact correct, let me show you that. We'll talk about some means by which we can do that. So what do we mean by Agile specifically? One thing we'll work iteratively and incrementally. So for example, system engineering will identify our use cases as elements of use cases, different usages of the system. For an automobile system, you might think about, well, there's the door system and managing the doors and door locks, there's engine control, there's infotainment, there's environmental control with, heating and cooling, and all of these have kind of functionality. We identify those requirements and we'll incrementally detail those and iteratively add more and more completeness as we move on. Depending upon our environment, our business, our industry, and our particular problem we're trying to solve, we adjust the work products. So Agile means we're going to do what makes the most sense, right? So if you're not doing something safety critical, don't do the safety critical workflows, right? If you can avoid doing something because it's not relevant, then don't do that, right? So it's about being agile and robust in the context of what you need to do and not doing stuff beyond the necessary degree of precision beyond what you need. And this is particularly true of planning. So monitor progress and adjust plans dynamically. So in the Harmony process, which we'll talk about later, we talk about dynamic planning, where we plan with a certain level of error bars or fidelity, if you will, knowing that it's not completely correct, but that's the level of information we have. And as we go through the project, as we get increasing information about our efficiency and the defect rates and how requirements and things are changing, we can improve those estimates. So we adjust our plans based on actual truth on the ground, based on actual measured efficiency and progress, right? So we adjust our plans dynamically, as opposed to ballistic plans, where we plan once, assume it's going to be great and correct for the rest of the project, and never ever update them. That is just a way to be wrong, right? So rather than ballistic planning, we do dynamic planning. For systems that are safety critical, high reliability, or security critical, which are most of the systems I work in. I work in aerospace and medical and those kinds of systems. These are concerns, and it's not that you do these things either at the start or at the end. You do them all the way through, because it's crucial that as you make technical decisions, as you make functionality decisions, you make technology decisions, that you have assessed that, yes, this is safe enough to meet my needs. This is reliable enough to meet my needs. So you have to do this all the time. Traceability is a key thing in those environments. And as data stabilizes, as a use case analysis stabilizes the requirements around some capability, for example, now we'll trace to existing architectural elements, back to the stakeholder needs, back to our safety analyses, and so on. As these elements stabilize, we do this incrementally, rather than saving it to the end and doing it kind of one big go, which is doesn't work that well in my experience. And probably the most important thing is that we verify the engineering data continuously as we create it. I think that's the thing that really makes Agile effective for system engineering, and that means we have to have models. because you can't really effectively verify work products if all you have is text. So engineering data, to my mind, means models. And there are kind of four underlying advantages. So first of all, you can look at different aspects of the system, structural, functional, behavioral, parametric, safety, and so on. And you can look at those aspects at different levels of abstraction, such as your system context, architectural level, subsystem level, component level, detailed design level, right? So you can look at those things and create views to analyze and understand different aspects of the system at different levels of abstraction. It provides a common language and tooling environment to do all of that work. And that's really an important inclusion. And you, again, can make provably correct statements about your system in terms of behavior or capability or functionality or performance or safety. So there are kind of five key important views. There are others as well, but I think that these are the really kind of key ones. First of all, structural views. There are functional views, whether these have to do with requirements and use cases and the relationships. Behavioral views, how do elements behave, how the structural elements behave and perform their work. How do they behave together, right, in their interactions? And then we also can model quantitative aspects such as performance and other kinds of constraint models. And we do that with parametrics, right? And all of these are done against the underlying integrated information that we create when we model. So, having said all that, MBSE sounds great. There are some difficulties people have had adopting model-based system engineering. And I've, again, worked with hundreds of companies, and I've seen people succeed famously and fail pretty, catastrophically doing this. And so I think that there's some issues that are addressable, but you have to address them. You have to come in with open eyes and say, I am going to address that issue. And if you don't do that, just try to hide, leave it, ignore it, it won't happen. That's not a recipe for success. So first of all, you have to understand modeling. If you're coming from a traditional environment where you got, Word and Excel, modeling, the idea, kind of fundamental ideas of modeling may be new. And they take a little bit of work to grok them in Heinlein speak. So we use tools to create and manage models, and those tools can be kind of complex because the models can be kind of complex, and they have to support multiple different workflows. So we also need to have skills with tools. So process means that we have a recipe for what we do, what we create, what we consume, and what steps we're going to do, and how we verify we're doing a good job, right? That's what process is. So if you're using different technologies, modeling, different tools, different work products, there's going to be some changes to your process. So you have to figure out how to adapt your process to incorporate models effectively. They're not the same as Word documents, right? You don't verify them the same. You don't capture information the same. So there are some differences. And finally, you have to figure out how you're going to adopt. So you've got maybe starting from a traditional environment, you got your Word, you got your spreadsheets and stuff, and you want to move to a model-based system engineering environment. How do you get from here to there? How am I going to adopt this? The thing you don't want to do is come in Monday and say everything's going to be different. Boom. That's, again, not a recipe for success. So we have a workflow process for adopting the new technology, adopting MBSE, and we'll talk about that. And there's a real challenge here, and how do I make this easy? And that's really the focus of what I want to talk about today. So first of all, understanding modeling. Let's focus on that issue. Text is easy, so why should I model? I can understand text. Text is great. I can write text. I can write poetry in text. Writing a poem with a state machine is much, much harder. Now, I have done that. My wife definitely appreciated the state machine poems I write her. They even execute, right? But it's not the natural language in which you capture poetry, right? It's not expressive enough, generally. So why should I model? Well, the example I like to give, and you may have seen this example if you listened to me before, If you suppose you want to design your dream home, so you go to an architect, and this architect then comes back with a specification. And this is typical for system engineering. You end up with some huge monolithic, Word document with thousands of requirements, such as these. Intended by 7 meters for the west corner of the premises, or the left corner of the house. Then entrance doors intended by 3.57 meters, 2.3 meters high, 2.2 meters wide rather, and 2.2 meters high. There's a left-hand hinge over the inside, and so on. So my question to you is this the house you want? How can you tell? How do you create the viewpoints that allow you to analyze this data and say, yeah, that actually supports the workflow where I'm coming in, I'm from a hard day at work, and I want to make myself a drink and sit back on the patio. Does that optimize that flow? Does it? Does it optimize heat management for the house? And you want to have an efficient, energy efficient house? Does it manage that? How would you know, right? So are these requirements accurate, consistent, complete, and correct, right? How can you tell? So you go to a different architect and he builds a model. So you've got this integrated set of data showing different viewpoints to answer different kinds of questions. So here the structural viewpoint for structural stability in earthquake areas. You can look at the layout, so you can see how you don't open the front door into the bathroom, for example, right? May not be obvious from the requirement specification, but from these views it is obvious. Okay, and you have things like water flow, heat capacity, and so on, energy efficiency. You can build these different models against a set of engineering data. This is why we model. You can answer those questions. Is this the house I want? Right? Much better than with just textual specifications. Having said that, the SysML language, which is like the de facto language these days for system engineering MBSE, is a complex language. I'm one of the authors of both the UML and SysML specifications, the original specification, and these are not simple. The UML specification currently is 1,050 pages. If you look at the 3 specifications that make it up. And SysML takes about 80% of that and adds another 250 or so pages. And this is some dense stuff. So it elaborates different ways of connecting system with ports, adding continuous behavior by elaborating activity flows, as requirements and allocations and standard units and parametric modeling and parametric constraints and constraint properties and all kinds of stuff, right? That's complex. So that is a kind of a learning curve, learning wall that you have to address. There are a number of views that are pretty common in system engineering. So we have use case diagrams, requirements diagrams. Those really focus on functionality of the system or its components. Block diagrams, there's a couple kinds of block definition and internal block diagrams that focus on structural elements and their relationships. Activity and state diagrams focus on behavior. Sequence diagrams focus on interactions, which is a kind of behavior, collaborative behavior. And parametric diagrams focus on kind of quantitative constraints. So all these are viewed, and there are also a bunch of different kind of tabular forms of data, particularly one who want to show details of data. For example, you want to look at a requirement. You want to see, well, so where does it come from? What stakeholder need does it address? Where is it met in the architecture? What test cases are going to, so those kinds of traceability tables or the metadata around that. So tabular matrix forms also exist to help you understand the details of these elements beyond just what's on the graphical views. So one of the first goals here, things you have to address, is you have to understand modeling by understanding the language you're going to use. Now, remember, SysML is a big, complex language, but you don't need all of it, okay? 25, 30% of it is enough to do most of the stuff you need. And you can incrementally add additional features as you need them, if you need them. You don't need to worry about tree studies. You may not need to do parametrics. If you don't have to worry about sequence reliability, you may not have to worry about those views, right? So we focus on the language parts that we need. We subset the language. This is a common thing. You subset the language to the parts that you need, right? I also highly recommend you get mentoring. Now, it's not just because I offer mentoring. You don't have to get it from me. But people, if you use a language in a new way, you will make mistakes because you don't really have a deep understanding yet. And it's nice to have someone there to say, don't go down that road. That will come back and bite you, right? And this is why. Someone who's been there, done that, can really help you come to speed quickly in terms of effectively applying the language. Now, Rhapsody has a thing called SysML perspectives that you can use, which are, if you will, subsets of the language. Now, the basic one is based on a profile I did called Minimal SysML, and advanced is everything SysML offers. And the other perspectives are based on kind of level and what you're trying to accomplish. So we have one for requirements engineering, one for architecting, and one for doing trade studies, right? And advanced, of course, includes everything. And so we kind of remove from the menus and the from the toolbars those elements that aren't relevant to that perspective. And so we simplify the language that is kind of before you, simplify what's in front of you. So the minimal SysML basically was a profile of SysML that I created that used somewhat fewer diagrams and simplified the elements you could put on individual diagrams. So for example, simplified ports. SysML ports, is a lot of complexity there, so we said, well, just have proxy ports and interface blocks. We won't have full ports, we don't have standard ports, we don't have flow ports, we don't have interfaces per se, we interface blocks. Similarly, we simplified state machines and sequence diagrams to the commonly used things. Now, it doesn't mean you can't add these if you have a need, but they're not, in your face, if you will. So just a couple of quick views here. Simplified block diagram, this is the block definition diagram. And just look at the toolbar difference between what's on the left, which is the basic one in the simplified subset, and the full one, which is on the right-hand side. So you don't have things like, problem relationship or conform. We don't have all the value types, dimensions, units, all the different relationships. You just have enough to do the basic block modeling. Okay. Similarly, for activity diagrams, and again, it's not so important. You look at, what's included and what's not, just that there's a big difference. You have to subset the language is the message. Similarly with, sequence diagrams, there are features for messages that were sent that didn't arrive, called lost messages, messages that nobody said, but somehow you got. Yes, there's a feature there for that. Action blocks, those sorts of things are omitted because they're not commonly used. In fact, they're almost never used. But nevertheless, they're there if you need them in those very specific circumstances when you want to model them. So again, simplify the language. Now, beyond that, you have to learn to think in models. It said that you learn a foreign language. If you're English speaker and you learn German, as you start out, you think in English and then you translate to German. And over time, as you get better, you start thinking in German, right? And it shapes your cognitive processes. So you have to think in models. First, you have to understand, a model is always an abstraction. By definition, a model basically omits details and unimportant things that you're worried about and focuses on details that you are worried about. So I want to understand engine output. I'm going to focus on details like how much fuel comes in, the efficiency of my chambers for the explosion of the gas. How do I synchronize the motions? I don't really care what color it is. I may not care what material it's made of, right? Those are important aspects in some context, but it may not be important to understand engine power output, right? So I build a model focusing on aspects that I think are important and omitting aspects that are not important. If it had all aspects, it wouldn't be a model, it would be a copy, okay? Diagrams are not the model, okay? People think of diagrams because that's the part they typically see. That's how you enter information into the modeling tool, and that's how you visualize information that's already there. That's how you create viewpoints to answer specific questions. That's how you build views to support different kinds of reasoning. But it's not the model. It's views of stuff that's in the model, right? So they're important, but they're not the thing. The thing is the model. And that model modeling aspect is really important to understand. Another key one is called the type instance dichotomy. And what this means is we have two kinds of things, and this reoccurs in many different areas. We see it in structural here, but also we see it in behavioral things too. Blocks are types, okay? Blocks are kind of classes, but they're types of things. And they have certain properties called features, as well as some other properties as well. And they define the properties of things that may exist in the real world. So blocks are types, but types really exist at design time. They don't exist in the running world, okay? That's how we think about them, but they don't really exist. What exists in the real world are called instances. These are things that exist in the real world that their properties are defined or specified by the types, okay? And so you've got these two things. You have to understand, are you talking about types or are you talking about instances? And there are places where that distinction is important. Let's just say that. So for example, here we've got a pump, and this pump has some value properties like flow measured in cc's per minute and pressure measured in pascals, and it's got some services around those like get the measured flow, get the measured pressure, set the commanded flow and set the commanded pressure, right? And then below that we've got instances, and we see the upper pump is of type pump, the lower pump _1 is of type pump. Those are instances, and you'll see those values have specific values at the snapshot, the instant of time when we took this picture, right? For example, the upper pump, the flow in cc's per minute is currently 475. If you look 10 milliseconds later, it might be 500, okay? So they have particular values associated with them, whereas the type doesn't. It has a range of values it can assume in the instance. Interfaces are specifications of things that are shared, right, and how you share them. And there's a couple of different kinds in SysML. We'll ignore that detail for now. But here we've got a couple of blocks. We've got a sensor block, and we've got a control system block, and they have a compatible interface. So over on the left-hand side, we see that the sensor has a port called client port, and this type of the interface, the little lollipop there, is called iSensor. And above, you see the services that you can invoke across that interface. Things like get flow, get temperature, set zero offset, and so on, right? Over on the right-hand side, we see this port called sensor port. And we see it also, it has a required interface, that it requires something else to provide those services. And so that's the socket, right? And so since we've got one side that requires this interface, the other side that says, yeah, I do those things, I provide those interfaces, they're compatible, and I can plug them together. But I can only plug together instances. So at instance time, I can create a particular sensor and create a particular control system, and I can wire them together so they can collaborate, right? An interface is the specification of what goes across there. And they can be services, they can be value, or what are called flow properties. So I can talk about if I'm modeling a flow across a valve, I can have a flow being a value that is shared between those, for example. And so that's what interfaces are. Fundamental concept of modeling. So let's talk about some of the best practices. One of the best practices is know why you're modeling something. You see people modeling stuff just to be complete, or just to be, because it's cool. But really, know why you're creating either a model element or a view of that element, such as a diagram or table. What traditional work product are you trying to replace? What information are you trying to capture or specify? What should this model element or view contain? And what should it not contain? What's in scope, what's out of scope? Okay? What is required fidelity or precision of the input or output? And what is the outcome? What do you want to use this for? What's the goal of doing this? So my recommendation, having seen lots of really horrible diagrams, is that every diagram you make should answer one specific question, show one specific concept, or support a specific line of reasoning. Show me the stuff around this capability. Show me the stuff around this architectural feature. Show me the stuff around this safety concern, right? Those are particular, build a diagram or table or viewpoint to show that, right? And it's okay then to have the same model element to appear on multiple diagrams because it has multiple views that are relevant to it. And I like to add a comment on each diagram identifying what its mission is. So here, for example, it's a diagram I did in a book I wrote a few years ago. And we see a comment here giving the mission statement. The purpose of this diagram is to show spatial reasoning among the ship, transport target, and inertial reference frame. That's its purpose. So it shows the structural elements and the relationships, the data elements and services relevant to that aspect. And if there are other properties or features those structural elements have, they're not shown here because they're not relevant to its purpose, its mission. And that gives you much more readable diagrams and views, much more usable diagrams and views. So here are some common missions. Show the elements of a package. A package is a model element that contains model elements. This is a way of organizing your models. Interfaces between like software and mechanical and electronics. Those are cross-disciplinary interfaces. Generalization taxonomies, a whole part taxonomies, system interfaces, structure of elements, collaboration structure, model organization, snapshots, and the architectural viewpoints, the subsystems, components and how they relate, dependability, which has to do with safety, reliability, and security, concurrency and performance and resource views, distribution viewpoints, deployment, how do I deploy things across multiple engineering disciplines, and then there are some subviews which might relate to one or more diagrams. Subsystem model organization, the task diagram, views to show how you can ensure there's no deadlock, how you're managing your resources, middleware, messaging protocols, hardware software interfaces, and so on. So there are many. So how do I ensure my engineering data that's held in my model is correct, complete, accurate, consistent, is a high quality? Well, there are three ways. You can review it, you can test it, and you can analyze it. So if all you've got is text, the only thing you can really do is review it, okay? So that's not a bad thing. I use reviews all the time, but they are the weakest form of verification. So there's two forms of it. There's syntactic verification where you say, so you say, our diagrams are structured like this. In the upper left-hand corner, we've got this mission statement, the diagram. If it's this purpose, if you have these things on it, it's a standard for how you want to model. QA can come in and say, did you meet that standard with these work products? And that's not bad. That's a good thing. Then there's what we call the semantic model, semantic verification. Is the engineering data actually correct, right? So it allows subject matter experts and architects and peers to identify issues with those work products. It allows verification of informally verified work products that you can't use other means of verification on. There are some issues. It's very easy to miss subtle problems in complex work products. It happens all the time, which means that when you actually get to building the system and verifying the system against the requirements, now you discover issues and problems, and you have this big issue of going back to your system engineering, re-specifying it, throwing work away and re-engineering the systems, or at least portions of the systems. Very expensive and very common. Effectiveness depends on the skill and attentiveness of the reviewers, and I've been in reviews where, for example, you look at a large-scale commercial aircraft, you'll have something on the order of 20 or 200,000 requirements. I've been in those reviews. They take months, okay? And your vigilance is pretty good for the first half hour. It begins to sag by an hour, and by the second day, your vigilance is really not that high, right? And so that's a problem. So it's a serious issue with vigilance. And it can be very expensive. So we have a process in the Harmony process based on Fagan inspections for a good way to efficiently perform reviews, but they can be expensive and they can take a long time and tie people up because they're not doing any other engineering work while they're in the review. Another thing you can do is you can test. So when you test, it means that you've got a system or a simulation of a system, of a work product, engineering data, and you want to verify certain properties by applying some data set to it in a certain order with certain values and certain frequency and timings with some certain expected outcomes. And you can actually, if it runs, if it's a type of computational model that executes, you can then actually test it. You can apply this, run the simulation or the system, and see what happens, right? And say, does that meet my expectations? So it's pretty easy to do, right? If you have simulatable models, and you can get arbitrarily good coverage. That is, you can increase the level of coverage by adding more test cases until you're tired of adding test cases. Cons are it can be expensive during testing. 60% of embedded systems cost is in testing of verifying systems. Higher levels of coverage can be expensive. So you look at safety critical systems that require things like MCDC coverage, modified decision coverage, right? That can be very expensive, right? And you can never be truly exhaustive because there's essentially an infinite set of different values, different orders with different timings. And it may function differently if you change the timing or the order or the values, right? It can never be truly exhaustive, but it's much better and much better coverage than you typically get with reviews. So I think they're complementary. You find different kinds of problems with the two different types of verification means. And lastly, you've got what we call formal analysis. It's a branch of mathematics that allows you to ensure certain quantifiable properties of systems. In some sense, it is the strongest means of verification because it is complete, but it's complete in a context of certain assumptions. And it is very sensitive to violation of those assumptions, which are called preconditional invariants. So for example, suppose I've got an elevator system, and I want to verify that I get an elevator request, that I can satisfy the request within 2 minutes in a given set of this number of elevators, in a building with this many floors, right? Okay, with this kind of traffic load, fine. But that assumes that the motive force, maybe it's motors or maybe it's the hydraulic system that moves the elevators, doesn't break. It assumes there's no electrical faults. It assumes that you don't have somebody holding the door open to chat with you when you're trying to get in the elevator and go somewhere, right? And it's very sensitive to violation of those assumptions, right? So there are downsides. Another downside is it's really hard to do. There are people with PhDs in this. So I worked on a project, for example, with NASA. We limited this to very small subsets of the problem because there's only so much time in the universe and our launch window is when it is, okay? So it's really hard to do. It's valuable, particularly on certain difficult problems that are difficult to test. So it's not like it's a bad thing, but you cannot do formal analysis of the entire system. It's just not a feasible thing at these days. There are also lightweight forms and other things like coverage analysis. So you can combine this with testing to make sure that you get a certain amount of coverage of your design, of your model, of your code, of your requirements. So you can do that. That's a lightweight form of applying formal analysis. And that has value too. So I talk about a computational model. This is the kind of thing I'm talking about. This is a GIF, obviously, but it's capture of an actual model where we've got below 3 different state machines, and the color coding, the pink states show the current state, kind of the green states show the last active state of these different elements. And above, we have a sequence diagram that's being drawn as the elements collaborate in this running of the system, right? This is the kind of thing I'm talking about. So I can say, well, if I have these state machines and these events come in these orders of these values of this timing, this is what I expect. I can capture the expectation. For example, it's a sequence diagram. I can produce the sequence diagram from the execution, and then I have tools that I can automatically compare them to see, well, are they the same or not? Semantically the same or not, right? There's a standard called UML testing profile, allows you to formalize this as well, that we support with a tool called Test Conductor. Okay, skill with tools. So we're talking about Rhapsody here. What I tell people is Rhapsody is a rich and powerful tool. And it's a little bit tongue-in-cheek, but the fact is it has a lot of features. And it supports a number of different workflows. So it's process agnostic. We're not going to lock you into our process. You can use whatever process you want. So there are many different ways to get something done. To simulate something or model something or to get to this aspect of data. So there are many ways to get there, which means that there's some tool complexity. So again, just like we subset the language, the perspectives subset the tool features as well. So that's one way, is you don't use stuff you don't need, right? And you can in fact hide it from your perception until you need it, then you can expose it by changing the perspective. You can also use automation. So Rapity comes with automation. Some of it's built into the tool when you just open the tool, and some of it is added when you add the Harmony SE toolkit, which is provided when you with Rhapsody tool. So you can use that automation. It doesn't really, it's nothing you can't do by hand, but it just automates commonly used tasks, commonly performed tasks. You can add your own automation. There's an API which you can write Java, for example, and access tool features to draw diagrams or pull data out or perform different kinds of data manipulation, create tables and stuff that you might want to do. Simplify your simulations by focusing on certain aspects. So when you do a full-up simulation with data and continuous behaviors and discrete behaviors and add all that stuff, you can get some pretty complex simulations. Well, one thing you can do is simplify the simulations. Maybe don't model the data flows, just model the control flows, if that's what you want to focus on. So you can simplify that as a way of simplifying the complexity of your usage of the tool. I really believe that, particularly for new groups, it's good to have a guru in your group that has extra training, extra skills, so you can go ask him, pester him with questions, and say, well, I tried to do this, and for some reason I couldn't get it. Can you help me, right? It's really nice to have something like that in your project. And the last thing I say is, it's like learning to drive a car. There's a reason why you have your teenage daughter get driver's ed. You don't just toss her the keys to your Mercedes, right? There's a reason why you do that, because mistakes can be bad, and you'd like to acquire some skills. The training is really helpful here. Okay, so I know you're all smart people and you can figure it out on your own, but you're not going to figure it out on your own without making some mistakes along the way. And you can just short circuit the time it takes to figure out that's a mistake and correct it by getting training. So what sets Rhapsody apart? We're talking about MBSE with Rhapsody context and making it simple. What's special about Rhapsody? So at a high level, this is the way I think about it. Rhapsody's focus is it's an engineering tool. Oh, and we use SysML and UML as the base language. Okay, that's the perspective. Most of the other tools, which we would consider competitors, I guess, they're SysML, UML tools. Oh, and you can use them to do engineering. And that drives feature sets. So Rhapsody really focuses on things like execution, simulation, collaboration with other engineering tools like requirements with doors and system simulation with Simulink and a bunch of other kinds of things. Right. So we support a number of languages, including DODAF and UPDM, which is UML for DODAF and MODAF. Computational and executable modeling is kind of a key core value. We want to make sure our engineering data is correct. How do you do that? We have to verify and validate it, like we just talked about. So Rhapsody supports those things. Simulation, and in fact, if you're doing software from it, you can actually produce code that you can deploy and ship with the systems. It's a pretty common thing. We've got built-in model checking, which you can extend if you want. There's engineering model verification. There's scalability to large-scale projects. You work on small project and large project. The biggest one I've worked on had 1,500 engineers using Rhapsody. So I know another project I know had 1,200 different Rhapsody models collaborating together for the large-scale system. So it scales up to large systems pretty well. You can support, as I mentioned, model-based testing with the test conductor tool, which is compliant with the UML testing profile. And we integrate with a wide variety of tools. So doors for requirements capture, rational team concert, which is a kind of an agile workflow management tool. Quality management, which is the test management environment. Realm, which is a interfaces to other kind of non-modeling tools outside of our outside of our normal portfolio. So you can build integrations, but how is this working with the CAD or PLM tool, right? And create views that integrate that data. Simulink, you can do hybrid co-simulation with that. Simplified handoff to software, because we also have a great software engineering environment in Rhapsody as well. So another view of what we mean, this is an activity diagram, and you can see things executing as the system runs. The little numbers, the little circles there are the pending tokens, because this is based on what's called token execution workflows. So we can actually model reasonably complex behaviors, actually very complex behaviors. This is just one that's a little bit complex. Certainly you can model stuff that's far more complex than this. Next, I want to talk about adapting your process. Okay, first thing is you don't have to use MBSE for everything, particularly if you're new to it. It's nice to pick some aspects where you might be weak, for example. So maybe you're pretty good with requirements, but your architecture really needs work. Or maybe you're really bad at safety engineering, or you know, really your control model is bad, or maybe your requirements are bad. What aspect is bad? Let's focus on that first, and we'll apply MBSE to that, and use traditional methods for the other parts. And maybe as we acquire skill there, maybe later on we'll add those aspects later. So I'm a big believer in incrementally adapting your process to focus on weak areas first. And different engineering organizations are weak in different places, right? They're strong, they have different strengths and different weaknesses. System requirements are a problem with a lot of companies. Functional analysis of those requirements, trade studies, traceability, quality of service, like performance or safety or reliability, constraint modeling, architectural design, or maybe you have quality issues, too many defects. Are you responsive to change, verification, handoff, validation, right? So typically when I do an analysis for a company, we'll focus on maybe 3 or 4 kind of levels of adapting the process. We have a kind of near-term, medium-term, and long-term things that we'll do to modify the process over time. But the key is you don't have to do everything different tomorrow. You can incrementally adapt your process. So I'm going to talk a little bit about the Harmony process. It's a process that I've created for both system engineering, in this case, the Agile model-based system engineering process. And there's another form of this for embedded software development, and they're integrated together at a place called what we call the handoff workflow. So this is what that workflow looks like. We're going to talk really briefly about this because we only have a few more minutes. If you look at system requirements, definition, analysis, there are details associated with generating the system requirement specification. In parallel, we analyze requirements around the use cases, resulting in update to the requirements or new requirements are identified. In parallel with that, we do our data schemas to understand the data and flows that are exchanged between the system and the elements in this environment. We analyze dependability, the safety, reliability, and security, and create a plan for how we're going to verify the system at the end. For architectural analysis, this is where we typically do trade studies to identify where can we achieve optimizations, and how do we do it, how are we going to assess the goodness of the solutions, that's the assessment criteria. We assign weights to this criteria, define the mathematical curves for that, assign the measures of effectiveness, and then determine the solution, which technology or approach is best, right? For the architectural design, then we're trying to focus on the allocation to the subsystem. We identify what the subsystem architecture is, allocate the requirements, build up use cases at the subsystem level, if they're complex. If they're not complex, then we don't need to do that. Update our logical data schema to add the new types we've identified, because now we're talking about inside the architecture. Create our subsystem requirement specifications, develop control laws across subsystem boundaries. Again, repeat our dependability analysis. So that's what we're doing in the architectural design. And then in the handoff, we go from these kind of logical viewpoints to the physical viewpoints and organize the data so that the different engineering teams can accept that. Typically, we hand it off to subsystem teams, which are interdisciplinary. They have the software, mechanical, electrical, hydraulic, pneumatic engineers, for example. So we build up a shared model to store the shared data is used by more than one subsystem. And they build up for every subsystem a subsystem model, with a deployment architecture. And that deployment architecture is how we allocate responsibilities to the engineering disciplines involved, software, mechanical, electrical, and so on, and allocate requirements and interfaces to those particular engineering disciplines. So as you adapt your process, provide guidance rather than leave your folks to kind of wallow around trying to figure stuff out. Provide some guidance. We have some guidance, and it's free, right? And there's some guidance where you can go buy our books, right? And I've written a couple of those. So if you have existing references, you might have to adapt them to take into account the specific workflows and work products for MBSE, but that's fine. If you've got a standard for architectures, adapt it for MBSE. If you've got a standard for requirements, adapt it to MBSE. We have a couple of these. One is the Harmony Desk Book. You may have seen this before. It's a little long in the tooth these days. Has been updated for a while. So I'm creating a new version, which should be out next month, called the MBSE Desk Book. And there's also modeling guidelines, a standard out that's freely available. You can also create your own process and modeling guidelines and work product standards. The desk will be available in a place run by a Rhapsody expert, a guy by the name of Andy Lapping. And there's a bunch of stuff there. If you're using Rhapsody, feel free to go there and look around. And the MBSE modeling standards, I'm going to have him, I don't know if it's up there or not now. I'm going to ask him to put them up there so it's available for people to download. And you can also customize our process if you like. A lot of companies do that. They take our process and they might use it as is, or they might adapt it. So the Harmony process is captured in a tool called RMC, Rational Method Composer. It's a SPIM compliant model. SPIM is the Software and Systems Process Engineering Meta Model. It's a standard. It's a standard way of modeling processes. And so we have this modeling environment full of processes called RMC. And you develop this model of it and you publish this, create views of it, and you publish it. And those views we saw before the Harmony process, those are what it looks like, okay? There are other views as well, but those I just showed you some of those. And then you publish it to engineers. So you can tailor the process and customize in the tool and then publish it for engineers. So you might, for example, omit areas of not concern. If you don't have safety critical stuff, fine. Don't include those things in your process. If you don't have stakeholder needs statements, you're starting out with system requirements, fine, you can omit the stakeholder needs. If you're not doing trade studies, you can eliminate it. If you're not doing control modeling, you can eliminate that. So that's one, you can just omit stuff that you don't use. You can also take the existing workflows, which are shown as these, kind of like activity diagrams, and you can simplify them. And again, there might be potential loss of completeness or rigor, but that might be okay in your environment. You can also just say, no, that's not how we want to do this other workflow. You can replace those workflows, right? So again, it's an environment which you can edit and manage the process. It's the process editing environment. And you can also employ the automation. So a lot of the process steps in the Harmony process are automated by this SE toolkit for model structuring, creating sequence diagrams from activity models, for creating ports and interfaces between elements, and so on. There's a bunch of functionality there. And these are just some of the views of the things. For example, you'll have the toolkit. You can create a Harmony project that creates a recommended model organization structure. You can import and export things, add various links and relationships, dependencies. There's a modeling toolbox. There's the allocation wizard. You can create sequence diagrams from activity diagrams. There's a bunch of features in this toolkit for automating things that you typically will do anyway, right? So you don't have to use them, but they're there if you want. Technology adoption, the last thing I want to talk about. I really believe that if there is a place to use Agile, it's in the adoption of technology, right? So the whole idea of Agile is do a little bit, verify you got it right, do more, okay? Kind of the core underlying workflow. So to adopt MBSE, do a little bit, verify you did a good job, add more. So identify what aspects you want to adopt. Is it use cases? Is it requirements modeling? Is it functional analysis? Is it trade studies? Is it architecture? What do you want to do, right? What parts of the language, tools, methods, and processes do I need to do that? right? How am I going to monitor that I'm doing a good job? Those success metrics, things like defect rates, engineering efficiency, right? Verify and validate. As you adopt, verify you're doing a good job, because a plan, a process is really a theory about how things should go. If it's not working as well as you like, tweak it, fix it, make it better, right? And then once you've done that, you've got it pretty solid. Now deploy it across your organization. You get the next aspect of modeling, right? So it looks like this. Start off with assessing, so what are your organizational objectives? What do you do now? And what are issues and problems with what we do now? Architect your solution. So where do we want to be? We want to use MBSE. When you have 10% of the defects we have now, we want to have 50% less time, whatever your goals are. What is the gap between where we want to be and where we are? Define those processes, practices, and tools. Plan for how you're going to adopt it. This is where I might come up with a medium-term, short-term, long-term kind of plans. How am I going to specify, how am I going to identify that I'm doing a good job or I'm not going to do a good job? What are my metrics of success? It's nice if you can run it in a pilot first. From my mind, a pilot is 6 people, 6 months, that kind of size. I worked with one aerospace company. They wanted to do a pilot with 300 people over 2 years. So pilot means different things to different people. But I think an ideal pilot is 6 people, 6 months. That's what I think. And then adapt the process based on success, these success metrics, tweak the process, and then you deploy it across the organization. All right. So I have written on these topics. If you'd like to know more, feel free to track it down, or go to Merlin's Cave, as I mentioned, and download some material there, or Google me. You'll find lots of papers and stuff on the web. With that, I'll return control back to you, Mark.
Thanks, Bruce. Really appreciate it. Question came in. I had some dialogue with the attendee, and I tried to answer it the best I could. I hope I was on the right track, but I thought I would throw it out there to you, and then maybe you can elaborate on it. And I had recommended that the person utilize Doors and then the Doors gateway, where they can do written requirements, transmit it down into Rhapsody, and the person who's using Rhapsody can then put the visual models into Rhapsody so that it corresponds with the written requirements. So here's the comment question. Aerospace industry requires models to be driven by textual-based requirements. In your experience working on many projects, how has this been efficiently handled without doubling the effort? For instance, creating text requirements and models. Is there some material available that defines a rule of thumb for differentiating what goes into the textual requirements and what goes into the model?
If only someone had written a book on this topic. Oh, wait, someone has. So I talk about that in actually a number of these books. So as a system engineering, I talk about that quite a bit. So yeah, so if you look at the standard DO 178 and its child standards, the C version of child standards, it says that you've got to have a specification model that comes from textual requirements, and you can build a specification model from that. And then separately, there's what's called a design model. So yeah, absolutely you want to have that. So here's kind of my view. Textual requirements are great. They're wonderfully expressive. They're easy for stakeholders to access, and they can read them and get an idea, although it might be ambiguous, but nevertheless, they get an idea. Models require more precision. Not everyone has the skill or inclination to learn a language to read them appropriately. So, but the problem is that I get to do a good job of my textual requirements. That's a kind of key issue. So this is how we connect them. We do our textual requirements. We group them into use cases. So around maybe infotainment on a car, or controlling my control surfaces on my aircraft, okay? Group them into these use cases. Now I create a model of those requirements, which includes sequence diagrams, maybe an activity diagram, maybe a state machine, simulatable, executable, computable model. And the reason why I do that is to discover, are my requirements consistent, complete, accurate, and correct? So every requirement, a textual requirement, is represented somewhere in that use case model. Sequence diagrams, state machine, activity diagram, maybe multiple places, okay? Because the purpose, the thing you're trying to do is, did I get all the requirements and did I get them right? Are they correct? Do they have enough accuracy and fidelity? It's very, very difficult to identify that just by reading the text. But in a model, it's much, much easier, particularly if you build a computable model. So the outcome of that functional analysis is identify, by far the most common thing is missing requirements. Oh, I forgot this. I forgot this case. I forgot this fidelity. I forgot this constraint. I forgot this performance requirement. Those come out as you do that detailed requirements model. So yeah, so you can use doors, what we call doors classic, and go through gateway and Rhapsody. You can do doors next gen and go through design manager into Rhapsody that way. You can, I know one group, the automotive group I just worked with in Germany a couple months ago. What they did is they actually kept all the requirements in Rhapsody itself, right? It depends on your needs. Most commonly, you'd have either doors to gateway to Rhapsody, or you'd have doors next gen to design manager Rhapsody.
Thank you, Bruce. I think that's it for the questions. I'll wait. Here we go. Another question just comes in. Is your basic profile for SysML and Rhapsody available as part of Rhapsody 8.2?
Oh yeah, absolutely.
Okay.
It ships to the product.
Okay, no more questions coming in. We're going to go ahead and wrap up. Thanks, Bruce. Really appreciate you presenting again. You've been very informative and very helpful in helping us and our clients. So with that said, everyone have a great weekend, and I look forward to having you come back again. If you have any further questions, just reply to my automated email. So with that said, the webinar is now concluded. Goodbye all, and take care.